two wires of the same material and length but difference in diameter. Now, if they are the same material, it means they will share the same properties, and then their diameter is 1:2 as a result of the same force. Okay, the potential energy per unit volume of the two wire when stretched is what? Since this is the diameter and we want to find the energy density as a result of this, let's find the relationship between the energy density or the potential energy per unit volume and the diameter. The potential energy per unit volume, which is the same as the energy density, is the half of the stress multiplied by the strain. The stress is force upon the area, which is the same as this, and the strain is this original length. Now, in this case, the diameter will be inside the area. The diameter will be inside the area. Since it's a wire, the area of a wire is pi r squared or pi d squared upon 4. That means we are going to have something of this nature: half, then force over pi d squared upon 4 multiplied by delta L upon L. It implies that the E is inversely proportional to the square of the diameter. That is, E1 will give birth to 1 over D1 squared, and then E2 will have its D2 here and it's squared. Okay, now if the ratio of the diameter is 1 to 2, let's say D1 ratio D2 is 1:2, it implies that D1 upon D2 is 1 over 2, which means that the twice of D1 is D2. So instead of D2 here, I will replace it with 2D1 so that I will have something of this nature. 2D1 squared upon D1 squared. So D1 squared get to cancel D1 squared, so that we'll have 4. So the relationship is 4 upon 1. It implies that the ratio of the energy densities is 4 to 1. Alright, let's solve another practice problem. Alright, given the strain as this, the strain, which is 0.05 percentage, 0.05 percentage, which is the same thing as 0.0005. Strain has no unit. The energy stored per unit volume, I got this by dividing this by 100 since it is in percentage. The energy stored per unit volume is what? Note that the energy stored per unit volume is half of the stress multiplied by the strain. It is also the same. I gave the relationship in my video on energy density of an elastic spring. Though it is also the same since stress from the formula for Young modulus. Since Young modulus is stress upon the strain, so we can say that the stress is equal to the product of the Young modulus and the strain. Since we have the strain, we can just substitute stress for Young modulus and strain strain multiplied by another strain, so that eventually you will have something of this nature. Half multiplied by y multiplied by strain squared. Then substituting half, this is the energy density or the energy stored per unit volume, half of the Young modulus of the material multiplied by the square of the strain, which is 0.5 squared. So if we do this correctly, we should have 250 100 joules. All right, not joules but joules per meter cube. Okay, make sure you check my next video and subscribe to this channel. Thanks.